Hello folks, this is Todd Coburn of Cal Poly Pomona with lecture 6 of Aero 3261. Today we're going to be going into a new idea of torsion on members, and we're going to focus first on circular members, torsion of circular members. Let's get started. Imagine a shaft being twisted. We've got a torque applied by the motor and it causes twist on the shaft. We're going to have torsion of the shaft, and that torsion is going to have to move through the fasteners, into the shaft, down the shaft, and back out through the other end. We're going to be studying the kinds of stresses and the angle of twist that this kind of loading can cause. So if we imagine first a long circular cylindrical member, imagine we've got this line on the side of it, as you can see here, and as we twist that, we see a deformation, a torsional deformation of the structure. We're going to make some assumptions. We're going to assume that our deformations are linear and elastic. We're going to imagine that plane sections remain plane. If you imagine a bunch of quarters stacked next to each other, that means they all rotate more and more. They all rotate the same amount. Between the two, they get the same rotation, and yet those quarters remain plane and parallel to each other, right? Those areas of contact. And we're going to imagine that they don't distort, and then we're going to imagine that our material is homogeneous, isotropic, and elastic, which means it's the same everywhere, it's the same in all directions, and it's acting down there in the elastic range. Okay. Now with these assumptions, if we trace a line on the side of this, as we see here, if we imagine this line from B to A, as we twist it like this, we find that this point moves up here and we get like a constant change. So with reference to our initial line, we end up with this. Now since we assumed that plane sections remain plane, we see this is nice and even as we move from there to there. Now we're going to focus on this end, on the right end of this thing, and we're going to look at how this thing behaves. You're going to notice, if we redraw this, we've got this length here and this length here. Okay? You're going to notice as we move, we can look between this line, between these two lines, we have a little angle. We'll call that gamma. And then from the center of this thing, we have another little angle. We'll call this phi. This is a little distortion, or the angle of here, shown here. And we know the tangent of alpha is going to be equal to this dimension here, ds, over, right, this dimension here, L. Now if this angle gamma is very, very small, then that's basically about equal to alpha. So alpha equals ds over t. Now that's true for small angles, and we're going to imagine that that's true with everything we do. We also have this down here. So this little angle here, gamma, that's the angle of this rotation from this perspective, we're going to call this, we're going to define that as our shear strain. Now remember, when we had strain, that was change in length over length, and shear strain is also that. It's a little change in a dimension over a dimension. But where normal strain was the change in length over length in the same direction, shear strain is the change in dimension over a perpendicular dimension, okay? So basically it's this little ds over L. Now this over here, this phi, is actually the angle of twist of the shaft. So when we talk about gamma, or the shear strain, we just need this little angle here. When we talk about angle of twist, we need this angle looking at the end of the thing. Now if we imagine along here, we have these little, as you see, as we go through the same rotation, if we imagine a little element on the original thing, once it rotates, we see that little element moves and it distorts. It ends up distorting like this, where this angle here is our gamma, or our shear strain, and our shear strain is equal to this dimension, ds, over this dimension, L, in that case. Of course, this is a little increment of length. We could call it actually dx. So this little ds over dx, that's our shear strain. Okay, so these are the basic ideas. We're getting a little ahead of ourselves, but this is what we're going to be studying here. So our torsion induces an angular twist, and a little square element like we see here on the second shaft on the left deforms into a rhombus, and we can see the shear strain is that little angle on the lower end. So once again, the length times gamma, we can see from trig, is equal to that radius. That radius of the end of the shaft is rho here, times phi over L. So we can rewrite it this way. So the shear strain is the change in length over length. The change in length is this little dimension from A to A prime, and that little dimension from A to A prime is basically, since S equals R theta, that's basically looking at the end of it, is that radius of the end of the thing, rho times phi. So we see this relationship between the shear strain and the angle of twist. Do you see that? Okay. Now, that same idea, looking at the same figure again, then we can find our shear stress under torsion. Since our shear strain is proportional to that, we know that our strain is equal to this. We saw this on the last slide, right? The max strain is going to occur out there at the extreme fiber. So if we look at this angle of twist, you see, if you imagine if we look at the end of this thing, since our shear strain is this radius rho, right? And this is the angle of twist phi, so rho phi is that little ds over L. You see that? That means if we look at the center of the thing where rho is 0, the shear strain is 0. If we look here where the radius is rho, the max radius, then that's where the shear strain is maximum. So we see that we're going to get a linear distribution of strain. The maximum occurs out here at the radius, and the least occurs, 0, occurs at the middle, and it's linear in between. That's going to get a linear strain distribution on the thing. And we're going to see through Hooke's law that that also gives us a linear stress distribution. So since from Hooke's law we have that the shear stress is just the shear strain times the modulus of rigidity, we can combine these two equations and we get this relation for the max shear stress. Now we're not actually going to use this for the max shear stress. We're going to use this to calculate the angle of twist. So if we look at the angle of twist, we can say, well, the shear stress on any little element, if we just say, okay, out here at some radius r, we have a stress on that little band. The stress times the area, which is 2 pi r, right, times the thickness, ds, is the force, and we can write that as a function of the torque. Or we can go here and say that the stress at any point is just from trigonometry, it's just the rho, the distance to that, over the max radius times the max stress, which we can plug in here, and this gives us a relation between the shear stress at any point and the angle of twist. Now we're going to actually rearrange that here as we look at this a little further. So once again, if we just imagine, so we know that our shear stress, if we look at this part over here, we know that the shear stress is changing from that, or the strain is changing as we go from here to right here, right? It's going to be 0 here where our distance, the radius, is 0, and it's going to be maximum here where the radius is maximum. If we look at some arbitrary radius rho, we can calculate the shear stress, the average shear stress at that point. Now, if we want the force on that little piece, let's call it the force P, it's going to be that stress times this circumference, so it's going to be tau times 2 pi r, or pi d, times the little thickness, d or dt, the little incremental thickness of that. That's going to be the force. The moment of that guy that causes is going to be that force that's acting out here times that radius. That's what we see here. That means for every little strip, if we focus on this little strip here, which has an average radius of rho, then the stress on that little portion, the average stress, times its area, which is 2 pi r times dt times rho, is going to give us the little moment that part causes. That causes a moment about the center. So if we look at our segment again, and just imagine it has a number of strips, there's going to be a little moment due to this part, a bigger moment due to this part, another little moment due to that part. If we add all those moments together, we get the total moment on the section. So we can continue writing it this way. The total moment is just the sum of all those, which means we're going to integrate all of these values. If we do that, we can write this way. Now we look at it and we say, okay, the angle of twist is a constant, the g is a constant, the L is a constant, but that integral of rho squared dA, that looks like the polar moment of inertia. If we pull that out and just replace it with a polar moment of inertia J, then we can find that the total moment, which we call a torque, since it's since the unit normal, since the moment acts down the normal to the surface and is causing stresses that are parallel to the surface, it's called a torque. So we have that torque is just phi j over L, which we generally write in this other manner. The angle of twist is just TL over GJ. This is one of those equations that you are going to probably want to memorize because we're going to use it a lot as we memorized Hooke's law. So the angle of twist is TL over GJ. Okay, now we can say, using our earlier expression for the shear stress, which we aren't going to use in that form, plug in our angle of twist, and we find this, that our shear stress is TR over J. In this case, we're using that rho as our radius, but that means that the shear stress anywhere, if we have a section like this one, if we have a circular section, we can say, well, if that's the center, then we can take the radius or rho to any point and calculate the shear stress with this equation. We can calculate it there or here or here or here. It doesn't matter where it is as a function of, in terms of the angle. What matters is how far away it is from the center. This says we calculate the J of the entire section, the polar moment inertia. We take the total torque on the section and multiply that ratio times the radius of any point, and we will get the shear stress. If we look at this again, we can plot the shear stress from the center to the extreme fiber, and we find out it linearly increases. By this relationship, the shear stress is equal to TR over J, where R is just the radius at any point. Now normally, we don't plug in all the radii from the center out to the outside. Usually we're just focused on the maximum stress, which is going to occur at the outside of this thing. The stress is going from 0 to the maximum value of TR over J if R is the max radius. Does that make sense? And if we want to know, for a given torque that's applied to this thing, right, for a given torque, what is the angle of twist that this thing will go into for the whole length of the part, as we saw before? That's given by this. We plug in the torque times the length of the thing times the modulus of the thing, the shear modulus, times the, or divided by the modulus, divided by the polar moment inertia. That polar moment of inertia, while this is the polar moment of inertia, what that means is this is the torsional constant, okay? What we're seeing here is the angle of twist is equal to TL over GJ, where this J is the torsional constant. Now we're going to want to understand that in the future, and the torsional constant for a round section happens to be the polar moment of inertia. We're going to find out for a non-round section that's not true, and it's not necessarily true for a other kinds of sections. Any round section, though, if we can calculate the polar moment of inertia and we know what the torque is and the length, we can actually calculate the angle of twist or the stress using these two key equations. We're going to use these equations a lot in this class, and we're going to see them a lot in industry if you do any structures work. So this is bread and butter kind of knowledge for the structures engineer. Now, if we have a non-constant section, these two are assuming that the section was constant from end to end. And regardless, we can take the TR over J and calculate the shear stress at any point along this thing. But if we have a section that changes, as this one shown in the lower right, to calculate the angle of twist of the whole thing, we would have to find out, first of all, how much does this first little piece, if you imagine this as a series, we break this into a series of pieces, you say, okay, this structure here, it consists of a cylinder like this, which has a torque applied from end to end. We can calculate the angle of twist of that, TL over GJ, where this is its length, and its J is based on its size. Then we have the next piece, which is like this, but actually you'll notice that the torque changes in the middle. So actually we can divide that into two pieces. We've got this first piece which has a length, and the second piece which has a length. So we can go the torque on this first piece times its L over GJ, and then the torque on the second piece times its L over GJ. Then we have one more piece. We have a new torque and a new section, and we can calculate the TL over GJ of that guy. Then we take phi from this, plus phi from this, plus phi from this, plus phi from this, add those mothers together, and that will give us the total angle of twist from end to end. If we want to know what the shear stress is anywhere, all we're really going to be focused on usually is the max value at this extreme fiber. And we can say, well, this first segment has a certain torque. We can plug in its max radius and its J. The second one has the same torque, different radius, different J. This one has a different torque, same radius and J as the one right before it. And this last one has a different torque, different radius, different J. Calculate that. And each of those will have their own stress. The max will be whichever one is maximum. Does that make sense? So those are the nuts and bolts pieces of information for torsion of circular shafts. Now, the polar moment inertia, then if we have a solid segment, just like we did back in statics, we can take the integral of the radius at any point to the little increment of area, which is just 2 pi rho d rho. And if you go through that integration, you find that the polar moment inertia for a round section is just pi over 2 times the radius, the max radius to the fourth. Okay? Now if you have, if we look at tubular section, then solving that same thing, we find the second equation is the polar moment inertia. And you can look in the back of the book of these or use it right from here. Now a couple other ideas, if we look down below, we see we already talked about how the stress distribution is changing in a linear fashion from 0 to its maximum value at the max radius. See how that's linear? And that's because we're assuming that our stresses are down elastic range. If we focus on a little element at the edge, like this, we see then that a torque like this is causing a shear stress like that. And since this little element is lying right on the surface, right? Since shear stresses are so romantic, those are going to be mouth to mouth, tail to tail, mouth to mouth. That's the little element. Imagine this little element here has a little width, a little thickness, and that's what we're drawing here. You see that? Here's a little increment of thickness, and that's what we're trying to show here, the same thing. Okay? So if we have a twist like this, we can imagine those little elements. An element down lower will have a similar distribution, but it will be smaller, proportional to its radius position. Got it? Okay. Now, if we have an indeterminate shaft, for example, let's say we have a fixed rod, and we have this angle, this torque applied to the middle. The question is, well, we know that the angle of twist at A and at B must be 0, but how much does it twist here at the middle of the thing? In order to calculate that, this is an indeterminate problem. So what we're going to have to do first is figure out how much moment, how much of this torque goes each place. In order to do that, we're going to need the J of each of these guys. What we can do is see that, hey, our first little shaft here, we can see we've got two shafts. One of them, if we break this up into two pieces from here to here, we'll call this our element 1 and this our element 2. Okay? We can see this first one under the action of this. Now what we don't know, we've got this torque here. Part of it goes this way and part of it goes this way. So we can say this is the reaction, the torque reaction at A, and then we have this other element that's like this, and we have the torque reaction at B. And in between, we have this torque that's applied, part of which goes each way. We're not totally sure which one, how much goes each place. We have the J of this guy, 1, and we have the J of this guy, 2. So we can say, well, the angle of twist of the first one is going to be TL1, T1L1 over G1J1. And the angle of twist of the second is going to be T2L2 over G2J2. Now we've got different torques, different lengths. We can see the lengths. We got the same G actually, and we got two different J's. So we can calculate our J, figure out our length, calculate our G. The only things left is the torques. We know that if this is rotating and this is rotating, but these are attached, that these angles of twist must be the same. That means T1L1 over G1J1 has got to be equal to T2L2 over G2J2. And we also know that our torque that's applied has got to be equal to the torque reaction at A plus the torque reaction at B. That gives us two equations, and we can take those. I'm calling these guys T1 and T2 down here and TRA, TRB up here, but it's the same thing. We now can use these two equations to solve for our unknowns, put those together. Does that make sense? That's how we solve these kind of problems. So that was a sneak preview. Here's our first equation. Here's our second equation. And you'll notice here, this draws attention to the idea, one that I kind of skirted over in the discussion. We've got our angle of twist in one, but the angle of twist in the other is going to be opposite of that, right? So it's a negative value. And we can combine those two equations to solve this problem. Now the next idea is the idea of torque and power transmission. Remember, we have that the force times the distance is work, and moment times angle of twist is also work, and therefore power is going to be work over time, or torque rotation over time, and we can introduce these relations. Our power then is just the torque times the change in angle of twist with respect to time. That d theta dt is just the angular velocity, omega, in radians per second. Power is directly related to torque through that angular velocity. If our torque is in foot-pounds, our power is in foot-pounds per second. We have this relation for watts and Newton meters per second. And we can see that our frequency then, remember frequency is defined as cycles per second, and that is the same for a shaft. The cycles per second would be the number of revolutions per second, and we define that as hertz. Somebody decided that we don't have enough units already, even though cycles per second and revolutions per second are fine. Somebody has said, let's come up with a new unit to talk about that. And somebody else said, gee whiz, another stinking unit for no purpose, that hurts. And that's why we call those hertz. Now it's useful to note that the relation between the angular velocity, which is in radians per second, and the frequency, which is in cycles or revolutions per second, is 2 pi times the frequency is equal to our angular velocity, and that gives us this relation here. Here's a little handy conversion factor. We aren't going to do much with these conversions, but you need to be aware because there are some problems where we may run into using those. Now, if we have a disturbance in the cross section, that will cause a stress concentration. We will handle that just like we handle our axial ones. We'll come out here, find an appropriate stress concentration factor curve. And in this particular case, if we have a keyway like this, or a change in rate in diameter like this, we'll come with our first R over D ratio against the D over D ratio and get our K. We'll calculate the max shear stress of the minimum section, TR over J, and multiply by this factor in order to get the max stress at the geometry change. Sound good? The other idea we need is the idea of strain energy. As we saw before, we can derive our strain energy. It's just going to be, we saw before, we start with this work energy relation, that the strain energy is just the shear stress squared over 2G and the change in volume. Since our torsional stress now is T rho over J, or TR over J, we can plug that in here like this, simplify like that. Note that looks like the polar moment of inertia. Plug it in like this, and if we have a constant, this is just T squared L over 2GJ. That means if we have a cylinder of constant diameter and we have a constant torque on the thing, the total strain energy is the torque squared L over 2GJ. If we have different cross-sectional areas, we can just sum up all the different pieces to get the total strain energy of the part. So if we kind of summarize everything we've seen about torsion of circular shafts, these were our assumptions. Our torque induced an angle of twist, and these were our primary relations. Our shear stress is TR over J. Our angle of twist is TL over GJ. Our shear strain can be written as the radius times the angle of twist over L, and we have these two relations for solid and hollow shafts. Got that? Now these are all valid for circular shafts that hold to these assumptions here. If we violate these assumptions, we're going to need more complicated methods. Usually we're just going to charge forward and use these anyway. Just being aware that we have now violated these assumptions, which means our answers will be less accurate, maybe totally wrong, depending. Also note that this is for circular shafts. If we have a non-circular shaft, like a hat section, an I section, or a rectangular section, or a J section, or anything like that, then this will not work. We're going to have to tweak it, as we'll do next lecture. And this was a relation for non-constant shafts. Okay, a word on torque diagrams. Now you should have learned how to make shear and moment diagrams in statics. And torque diagrams are the same way. Whenever we have a shaft with multiple torques, if the torque is constant, we don't need a torque diagram. But if the torque is changing, it can be very difficult to keep tabs on what the torque is at a given point. Now, since our stress means we need to understand what the size of the thing is at the point we're getting the stress, and our angle of twist means we're going to need to understand both size, material, and torque information for each section. It's important to use torque diagrams when our problem has too much information going on to keep tabs of it easily. This particular case, now these are not totally clear. These little forces are causing torque. All these forces are applied out at some radius, and that's causing a torque. And so if these are applied out at a radius causing a torque, we can see that the torque from the first point to the second point is one value, change the next value, change the next value, and change the next value. This is our shear diagram for this, and our moment diagram. We're going to be getting into these later, how we develop shear and moment diagrams. But our torque diagram then would be, if we note that these are off at different diameters, then the torque will be like this 80 pounds times 4 inches would be the inch pounds. On the second one, it's 110 times 8 and so on, and we can write a torque diagram in the same manner. We have a driving torque. It's equal to whatever is coming in, and it's being sucked out through these three pieces, assuming these two bearings have no resistance. So we can see We already should have learned how to make shear and moment diagrams as we did in statics, like the first two, and now we're adding the idea of torque diagrams to our tool base. Let's look at some practice problems. Let's say we have this shaft, and we want to know the angle of twist. The first thing we're going to need to do is understand the torque. It looks like we have 6 kilonewtons, right, like this, which then jumps up to 20 kilonewtons, which then drops to minus 6 kilonewtons, and then is taken out with the last reacting torque. So we can draw a torque diagram. There's our loading diagram, and we can draw our torque diagram like this. See that? We're going from 6 to 20, back to 6 and 0 after that. Now that we know what our torques are, we can actually analyze the thing. And if we have different things going on, it looks like BC is hollow with those diameters. A, B, and CD are solid of diameter D. This is just a tricky question. We want the minimum max shearing stresses in BC and the required diameter of A, B, and CD if this allowable is valid. This is our basic approach here, and this is how we solve it. Once we have determined our stresses, our torques, that's what they're doing here, is they're just calculating the torques, which you can nearly see by inspection. We're going to calculate our polar moments of inertia of this thing, of the hollow and solid shafts, and then we can go and calculate our stresses and the angle of twist, and plug in our allowable in the equation of the corresponding shaft to solve for what diameter is required. So that is how we handle torsion of circular shafts. Now, it's important to understand this. Our next 2 lectures are going to build on these concepts and show how this plays out for different kinds of sections. This approach we just had is for circular round sections, whether they're hollow or not, it works. And next time we'll go into non-constant sections. Enjoy.